1,000 subscribers. Whoever would have thought that day would come? Certainly not me, but I guess we surprise ourselves sometimes. This is a compilation of my most viral YouTube moments and most viral YouTube videos, so you can sit back, relax, and probably learn something. Also, I do have a proper 1,000 subscriber special coming up, but I was kind of not expecting to hit this for another couple of months, so that's a couple of weeks away at the bare minimum.
This is a lithium battery, and they can be a great source of energy for many projects. The best part about lithium batteries is when they run out of energy, you can simply recharge them. However, this isn't as simple as just connecting them up to a DC power supply. You require a special type of charger, and that's what we're looking at in this video. Most chargers use something called two-stage charging, which, as the name suggests, consists of two stages. The first stage is a constant current stage. The second stage is a constant voltage stage. So what does this look like in practice? During the first stage of charging, the battery voltage increases at a linear rate, as you can see on this graph. However, when the battery reaches about 80%, it will reach its maximum voltage. At this point, the battery charger switches over to constant voltage mode, where it maintains a constant voltage by modulating the current. If we now add the current to this graph, you can see at that point around 80%, the current drastically decreases and eventually goes to zero when the battery is fully charged. Now that we understand battery charging, let's take a look at some chargers and see how they do it. In this video, we're going to be looking specifically at single-cell USB chargers. They look a little something like this, or if you buy Chinese, a little more like this. But these are quite small and difficult to see what's going on. So with help from my friends at PCBWay, I have made this big one. These chargers all revolve around a component called an inductor, which is this thing here that looks like a coil of wire. The symbol for an inductor is this squiggly line, which represents the coils of wire in it. However, I don't really see it. An inductor is an electrical component that smooths current by modulating voltage. The formula to calculate this is V equals L di divided by dt, where V is the voltage change, L is the inductance in henries, di is the change in current, and dt is the change in time. The only thing left to do now is build a circuit to do this. In our circuit, we have an input and an output. As we don't need our converter to be isolated, we can connect the negative wires of the input and output together. In this configuration, there are three ways we can connect our inductor. We can connect it across the input or across the output, but we can also connect it between the input and output. Let's now consider how we can build a converter. We need to initially connect our inductor between the input and output. During this stage, the inductor will charge up with current as it tries to stop the current rising. During this stage, the voltage will rise following the leading edge of a sinusoidal curve. Once the inductor charges up, we can disconnect it from the input and connect it to the output. This way, the inductor tries to maintain that current and forces voltage from the negative to the positive. During this stage, the current across the inductor decreases, as does the voltage, which this time follows the falling edge of a sinusoidal waveform. If we repeat this process over and over again very quickly, you can see how we can quite easily get a lower voltage at the output. As long as we don't let the current hit zero, the average voltage will follow a more or less sinusoidal waveform with an average voltage given by the formula Vout equals Vin times time on divided by time off, where time on is the time the inductor is connected to the input, and time off is the time the inductor is disconnected from the input. Now the only thing left is to work out how to turn it on and off. Luckily, we can do this with two electronic switches, by connecting one between the input and the inductor, and the other between the negative and the inductor. For these two switches, we can use MOSFETs. However, we can actually simplify this even further by using a diode in place of the second switch, as it only needs to block current in one direction. While the MOSFET is on, the diode will become reverse biased and it will block current flow. However, when the MOSFET is off, the inductor will draw power through the diode, making it forward biased and allowing current to flow. Now if we take a look at our board, we can see all of these components. The MOSFET is here, the diode is here, and finally our inductor is here. In addition to this board also has two sets of capacitors, one on the input and one on the output. These serve to smooth the voltages and stop any spikes or dips occurring. On the right here we also have some control circuitry to make it slightly easier for me to control it. It's not important for this video, so we can safely ignore it. The only thing left to do now is build a circuit to turn that MOSFET on and off. A lot of chargers nowadays just use a microchip for this, but there is actually a way we can do this with no computers at all, and it revolves around a chip called a comparator. A comparator is an IC that compares two voltages and outputs either a high or low signal based on which one is higher. By using this output to control the MOSFET, we can control the output voltage. But how? Consider this, we connect a voltage that we want on the output to the positive input of our comparator. We then connect the output of our converter to the negative input. When the voltage output is below the voltage we connect and want to have on our output, the converter will turn on and thereby increase the voltage. Once that voltage goes above the voltage we want, the comparator will turn off, and as such the voltage will decrease, and so on and so forth. The cycle will repeat. Okay, so now we understand how to make constant voltage, but how can we make a constant current? We can actually use a very similar trick. If we connect a resistor in series with our converter, there will be a voltage drop over that resistor, correlated to the current according to Ohm's law, which states that voltage equals resistance times current. For example, if we use a 1 ohm resistor, we will have a voltage drop of 1 volt per amp. We can use this in our converter from before, by using this as the input for our comparator instead of the voltage of the output. In this configuration here, by applying 1 volt to the comparator, we get 1 amp of current from our converter. Finally, we can use an AND gate to make sure both these conditions are met before turning the MOSFET on. I'm in a field, yet I have a completely functional computer set up. Well, minus a keyboard, because I kind of forgot to bring one. And because I know somebody's going to say in the comments that I was cheating and I use external power, because see here, it's also. So, how am I doing this? Well, it all comes down to this guy over here, which is what we'll be building in this video. This idea came to me when I found myself in possession of this battery. I was building it for a customer, but they cancelled the order before I was finished. I'm now stuck with a 12 volt 20 amp hour battery that I have no use for. And after brainstorming a couple of things, I've decided I'm going to build a portable power station with it. So what exactly is a portable power station? Well, it looks something like this. And this particular unit was graciously sent over by All Powers, and I'll put a link to them in the video description. It's basically just a giant power bank that you can run 240 volt appliances off. So how does one work? Well, for that, we're going to have to go over to the whiteboard. So how does a power station like this work? Well, it's actually much more simple than you might think. You have a big battery, which stores all your energy. This battery is wired into something called an inverter. Now, the inverter's job is simply to take DC power and turn it into AC power. You then feed that through a transformer to give you your desired output voltage. You also have a charger to charge up this battery. It's very simple at this stage. Let's take a deeper look at each individual component. I'm going to explain an inverter now, and if you don't get it, that's perfectly fine. It won't affect you in the rest of the video. So, how does an inverter work? Well, you have a timing chip, like this one, the 555, which is one of the most common timing chips on the market. That generates a pulse here, which is a square wave that looks something like that. That pulse then goes into two MOSFETs, an NPN and a PNP. Why are they different? So glad you asked. The NPN will turn on at this point in the sine wave because the voltage is flowing the correct way. But then, at this point in the square wave, the PNP will turn on and the NPN will turn off, and so on and so forth, thus generating that AC current. That's then going through this transformer and giving us AC power. And while you could build your own, like this, mine is sub-ideal because it gets too hot at around 150 to 200 watts. So for that reason, I'm going to order a pre-made one off of eBay. Well, eBay has at least shipped me a package. Let's crack it open and see what's inside. Okay, righto. This seems to be what I ordered. Real quick interlude. It started raining like all hell, and I had to go out and move everything I'd left outside inside. Sorry about that. There was a brief tropical storm, which kind of caught me by surprise. I've gone and dealt with that now, and I'm back. Let's test this thing. In order to test it, I've hooked it up to my battery by the method of holding wires onto this socket thing, and I'm going to plug in my amplifier and see if it works. At this stage, what? Oh, wait, is it on? I've just realized I'm going to get copyright striked for that song, so here's a royalty-free song. Myself, looking in my name, taking hold of myself. I pour a shot in a glass, take a sip, take a swing. So the inverter works. That's a definite positive. This means we're only missing one part of the entire system, and that's a charger. Fortunately, the customer has allowed me to keep his charger. And I'm sure this is a very good charger because the name is 12 volt 3S charger for lithium ion switching power supply. There is one issue now, and that is the size. Because there's no way I'm packing all these boxes into a nice package. So, instead, let's crack them open and see what's inside. To begin with, I opened up the inverter and discovered that it's actually a lot more simple than you would think. There's just two plugs and the inverter circuit board. The charger, again, was much more simple than you would think. Unfortunately, this particular charger had no safeties, so I would not recommend using one like this. With all the parts extracted, I needed somewhere to put them, so I 3D printed a case to store them in. I used PETG to print this as it's typically more robust than PLA. Now that I had a box, I had to do the internal wiring. I began by soldering the output of the battery to the input of the inverter. However, I soldered a switch on the positive terminal of the battery to allow me to turn the whole power station on and off to stop wasted power while I wasn't using it. I then attached the output of the inverter to this universal plug socket. I soldered 2 black wires to the socket first before putting it into the faceplate to allow me more room to work with. Bearing in mind this is AC power, so the orientation of the wires does not matter. As my next port of call, I soldered the charger to the inputs of my inverter, being very careful to use the correct polarity. By soldering directly to the inputs of the inverter, I'm able to use the switch to turn on and off the charging and stop leakage power going into the charger. In an ideal world, you would use a relay for this so that the charger could turn on when it was plugged into power. Unfortunately, I don't have a compatible relay, but I don't think it'll matter too much. At this stage, I also affixed a voltmeter to the front of my case in order to more or less be able to tell the charge level. With all the connections made, I heat shrunk every connection in order to ensure that there would be no short circuits and hopefully save me a fire. That being said, both the battery and inverter do have built-in short circuit protection as a safety. With all the electrical joints now complete, I securely attached all the parts together in the orientations and positions they would go in the final product. In order to do this, I used some thick gaff tape, or Gorilla Tape as you Americans would call it, and it holds them very securely in position. At this stage, I placed it into the box, but I used a generous helping of contact adhesive to secure the battery into the case and hopefully stop any movement. I had a small amount of difficulty fitting all the wires and cables inside the enclosure in a way that made sense, but with a little bit of persistence, it wasn't too hard. The final thing I did was 3D print a rubber sleeve to stretch over the outside of the case and make it look slightly nicer. And with that, the project is done. Hi, it's me in the present / less of the past / future relative to when I made that video. And basically, I get to now highlight how good this is. So as you saw in the intro, it does power a full computer system. But there are lots of devices out here that do similar things. So why is mine special? Well, let's take it inside and compare it to a competitor with the same capacity. So how does this compare to the AllPowers we looked at in the beginning of the video? Well, it's smaller and it's lighter. However, it does only have one power output, whereas the AllPowers has 2, as well as several USB outputs. It also doesn't have any of the fancy features like Bluetooth and smart power monitoring, and even a battery gauge. That being said, if you do want to undertake this project, it was really fun, and I would recommend doing it if you have the technical know-how. Just be wary, because you are working with high voltages, to be careful that you do know what you're doing, and you don't accidentally shock yourself. It's summertime, which is awesome. It's finally warm, but maybe a little too warm. And sleeping in a pool like this, as cool as that would be, I would probably drown. That means I need to find some other way of chilling off at the end of the day so I can go to sleep. Now, I've always wanted one of those Dyson bladeless fans, but it turns out they're like $1,000. and I don't have like $1,000 to spend on a fan. So instead, let's build one right now. Before we can build a bladeless fan, we have to understand how they work. So here's a basic understanding for you. Let's say we have some fluid running down this pipe. Doesn't matter what it is, as long as it's moving in the direction of the arrows. That is going to create a low pressure area at the side of the pipe joining it in, which means anything in this pipe is then sucked into the tube. This is called the Venturi principle. So how does this apply to a bladeless fan? This is a cutaway of a Dyson bladeless fan. Basically, this is a side of the loop. What we experience is the air is blown out from a slit on the edge of the hoop, and it goes in a direction kind of like this. And that air is sticky, and it sucks in the air in the middle of the fan. So you think of it as a very short section of pipe. We get the air moving in the pipe, and then that sucks in air from behind, because air wants to fill in the low pressure area which is created at the back of this fan blade. And that is how we have a Dyson bladeless fan. Now all we need to do is build it. I started off by designing it on paper and then scanned it in really badly. I'm an engineer, not a scanning technician, but I've upped the contrast and it's visible. I then designed it using Fusion 360 in CAD so that I could 3D print it, and then sent it over to my 3D printer, which did a nice job of building the components up for me. With the 3D printing done, it was time to move on to designing the electronics. In order for our fan to work as a fan and not just look pretty, we need some kind of internal electronics. So here's what I've designed. We have our USB-C port, which we're using as our voltage input. That is wired into a PDC004-PD, which is basically a fancy thing which tells the charger exactly what voltage we want. Out of that, because of this resistor here, we're getting 15 volts, which I wire into this charger here. This charger here gives us 12.6 volts to charge our battery. This is a very simple BMS, basically stops it exploding, nothing more. Out of our battery, we then put the power into this 40 amp joint ESC, which will control our motor. Unfortunately, ESCs don't just power things by themselves, so I needed some circuit to control it. For that, I've got this circuit down here. Basically, the way a drone ESC works is every 20 milliseconds, it receives a pulse between 1 and 2 milliseconds. This pulse, if it's 1 millisecond, is fully off, and 2 milliseconds is fully on. It's gradual in between that, but that's basically how it works. This uses a timing chip and a potentiometer to make it the specific length that we need for the pulse. All that's required now is for me to order the parts and assemble the electronics. This is not as easy as it looks. For some of the parts I could order them off AliExpress. However, for the large majority of them I couldn't. So for those parts I had them made and assembled at PCBWay. I'm not going to waste my time trying to solder tiny components onto circuit boards when I can just get someone who can actually do it with the proper equipment. So they did it for me. As for the battery I'm using, it's 3 21700 cells from a Chinese company that were very cheap. They have a rated capacity of 5000 milliamp hours. You're probably thinking, Boris, why are you using a battery? I mean, fans are always plugged in, right? Well, personally, I think battery-powered things are cool. Also saves me having to use a capacitor to start the motor up, which is better because I always shock. Sadly, it had a super annoying LED on the board I got from AliExpress, so I just desoldered it and everything's fixed. No more LED. With it desoldered, I gave it a go to make sure it worked, and then secured the motor in position using screws. Now that we've secured the motor in position, we need to build and design some kind of fan. The original drone propeller won't work because it will spin incredibly fast and just create turbulence. It does not have the static pressure needed for this scenario. To solve that, I've gone on to Thingiverse and I searched up high static pressure fan. I got this one, which was free and looks absolutely awful. I will still test it though. I then also got this, which is a computer fan kind of design. I don't like the fact that it has the same pitch the entire way along the blades. So I then opened up my software and designed my own. Now this one gets wider towards the end of the blades, has aerofoil shaped blades, and decreases the pitch the further out from the centre it is. I think mine's going to win the which has the most pressure scenario, but we'll put it to the test. Here's the basic setup. We have a scale and we have our fan blade here. I've limited the amount of air that can get in underneath. Basically we're going to see which pushes down hard enough with limited airflow. Let's give it a go. This is the free model from Thingiverse. Hovering between about 19 and 20 on the worst one. Next, computer fan. A surprisingly similar showing from fan 2, although slightly worse than fan 1. Competition's been done there. Yeah, I'm sorry, Thingiverse, you've lost. Wow, well that was quite a victory for my fan design. I was expecting maybe 5 to 10% different between them, but I guess I'm just that much better at designing fans. Now that we have a fan though, it's time to build the entire thing and put all the 3D printed parts together. And to hold the fan together, I decided to use this liquid nails type glue. Unfortunately for me, it turns out the people who manufactured it can't manufacture a silicone dispensing tube, so it ended up bursting and being a massive pain in the arse, so I just stuck my fingers in and scooped it out. After that, I added a bead around the top of the loop, as well as a bead around the base of the loop, securing it to the base of the fan. And with that, the fan is basically done. It's just a question of tidying it up and making it look nice. Yo, it's done. Check this out. I've actually gone back and 3D printed this knob, because I thought, well, it's a bit boring having this little black one, so it's a lot nicer like this. I've also added this little USB-C port in the back so that you can easily unplug and plug the cables. Should have really included something to indicate whether it was charged or not, but hindsight's 2020. Let's test it. I thought that the best way to test this was by taping some toilet paper to it. Oh well, what do you know, it blows toilet paper. What a massive surprise. Anyway, it's still pretty cool, basically proof that it works. And the design isn't too shabby. Vaping has become a massive problem. Each year, millions of people buy vapes and use them. I hate vaping so much that I think it should be banned everywhere in the world. The vapes themselves, once they're used, are often disposed of incorrectly in bins or just left on the ground. This can leach harmful chemicals into the soil from the lithium batteries inside them. Many times those lithium batteries could be reused, and that's what we're going to do today. By using a collection of old vapes, we're going to turn them into a power bank. Before we go any further, I do have to make a disclaimer. Lithium batteries are extremely dangerous, so be careful when you're using them. I do not recommend using them unless you have the knowledge and tools to do so safely. I am not responsible for any injuries sustained to your person while working on or following along with this project. Alright, let's continue. There are many different types of vapes on the market, and they have many different types of batteries. For safety reasons, I recommend only using 18650s, and in my experience, the best vapes to get 18650s out of are the ones that are rectangular shaped. After you get the batteries out, they'll probably have some kind of nickel strip on the end. You want to remove this. Now, there's no easy way of doing it. Some people use a Dremel. I find if it's cheaply made, like a lot of the Chinese ones, it's easier to just pull it off with pliers. Next, take a look for any swollen or damaged cells and dispose of them safely. After doing that, check the voltage of your cells. You're looking for between 3 and 4.2 volts. The next thing, and I cannot stress this enough, only use like cells. You're looking to collect at least 8 batteries for this. Don't worry if it takes some time. In order for me to collect this 8, I had to go through a few vapes. I'm planning to wire these cells in a 4S configuration, which should give me a total voltage of around 15 volts. I'm also planning to wire them with 2 in parallel to increase the capacity. So in total, this will have a capacity of just under 100 watt hours, so it will still be legal on planes. Disclaimer, do not take this on a plane under any circumstances, as you don't know the quality or condition of the cells. The next step then is to join our cells together into a battery. So let's try and get that sorted. Before we can build our battery, it's important that we balance all our cells correctly. Otherwise there will be a sudden inrush of current when we connect them, and that can damage the cells or worse, cause a fire. Ideally, to do this, you would have an 18650 charger. But if you don't, like me, here's a quick tip on how to do it. Take a piece of nickel and short out the negative sides of your battery. Then, using a 10 ohm resistor, short out the positive sides of your battery. Afterwards, be sure to measure the voltage with a multimeter to ensure that all cells are balanced correctly. Note this process may take some time, so be patient. In order to connect the cells up, you want to use this configuration to make it as compact as possible. These grey bars here are what we're going to use to connect the batteries, and I'll explain that in just a minute. But before we get there, make sure you do hit the subscribe button so that I can keep making these videos. Alright, gotta love a good bit of self-promotion. But in order to join these cells together, you're going to need to get 2 things. First is a nickel strip, and the second is a spot welder. Now, you can get these quite cheaply online, but don't buy really cheap ones, they don't work. As a general rule of thumb, you're looking for something that can provide at least 150 amps. But you need to know how to use it. And the correct way to use it is to place the contacts or the electrodes on the nickel strip before applying a current. If you do everything correctly, you should end up with a battery that looks a little something like this. But we can't use it yet, because without a BMS, it's quite dangerous. Lithium batteries, even brand new ones, discharge at different rates. And this means one cell will hit empty before the others. If we keep trying to discharge, well, you know what happens then. Obviously not ideal, but if we have a BMS in place, as the first cell hits empty, the BMS cuts off the power from the battery, stopping us discharging it any further. Good BMSs, like the one I have here, also have a feature called active balance, which means that it will take the voltage in the higher cells and give it to the lower cells. This basically means that you will get the most out of your battery and keep them as balanced as possible. Unfortunately for us though, BMSs have wires coming off them. And we can't use those wires to connect directly to our battery pack. So I need to solder those wires onto bent pieces of nickel strips, which I can later spot weld into position on our battery. Wiring of the BMS is very important. So let's take a look at what it looks like. We have two voltage ratings for each point. One is the nominal voltage rating. That will be 3.7 volts times the number of cells from ground. And the other is the fully charged voltage, which is 4.2 volts times the number of cells from ground. You can see here a wiring diagram for this particular battery. Now ours goes round in a circle, but you could imagine if it was linear it would look like this. We start by wiring ground, or 0 volts, to the flat side of the first set of cells, and then 3.7 volts to the positive side of that same set, and so on and so forth until we wire all the cells in. Now that our battery is complete, we can start adding the accessories required for a power bank. I'm going to be using this USB-C charging module, as well as this USB PD and QC charge module. This is capable of providing up to 100 watts. It's a great little module and I would recommend it. Unfortunately, we can't simply solder these directly on. We need to make a wiring harness. And the way I'm going to do that is shown on screen now by wiring the positive and negative of the battery into a Y splitter, so I can attach it to both this module and the charger. But this charger doesn't automatically switch off, so we will need to have the inclusion of a switch. With all my wiring done, I 3D printed a case, attached them in, and this project is basically complete. And just like that, I've turned something useless and horrible for the environment like vapes into a super cool, handy and portable device. Next time I'm out, I can charge my laptop, I can charge my phone, I can charge anything I like off this one device. It has up to 100 watt charging and supports QC 4.0 and PD 3.0, so it can do every charging standard there is. So, next time you're vaping, think, is it good for the environment, or could you be doing something better with those resources?
If you're still around, thank you so much for watching, and we'll get back to normal content after this.